When we're thinking about multiplying complex numbers, essentially what we're doing there is an application of the distributive property. That is, often foiling. Because what we're doing is very much similar to multiplying linear terms. Well, you've got to follow that first, outer, inner, last pattern, or whatever it was that you happen to remember to know how that works. But understand how that works, as always, nothing like examples. And that's what we're going to get. So for our examples here, we want to multiply the complex numbers 4i times 3 minus I and 2 plus 5i times 7 minus 3i. So for that first case, for that first one, there's not a whole lot of foiling that needs to be done because the real part of the complex number 4i is 0. I mean, you could throw the 0 in there if you want to practice, but a lot of stuff's going to die, and I don't know how you feel about that much death. So I'm not going to bother with it. When I'm dealing with this 4i times 3 minus I just go piece by piece. So 4i times 3 would be 12i, multiply 4i times negative I, and this is one we have to be a tiny bit more careful with, not too much, but just a little bit more, because what we would have there is negative 4i squared. And you have to be careful about what I squared is, because remember, I is negative 1, so we would have 12i minus 4 times negative 1. And if we want to put this in the standard form, a plus bi, we can actually turn that around, multiply in the negative 1, and what we will get, up to my ability to draw an equal sign, which is apparently limited, is 4 plus 12i. Now, in the second case, we're going to have to deal with that again. We also have a bit more to get there, because now we have to actually FOIL. But that's not so bad. It's still the same sort of problem you did way back when we first learned this. It's just you got i's instead of x's or whatever. So we have 2 plus 5i times 7 minus 3i. And for that, first, 2 times 7 is 14, outer, plus 2 times negative 3i, inner, plus 5i times 7, lasts, plus 5i times negative 3i. And then from there, it's just a cavalcade of simplification. So 14 remains 14. It's good at that. 2 times negative 3i becomes negative 6i. 5i times 7 becomes 35i. And then down there, the 5i times negative 3 becomes negative 15, but the I squareds become a negative 1, and as a result, we are left with positive 15. So, because we like to simplify this stuff all down, I mean, technically speaking, this is correct, it's just unhelpful. What we would end up with is 14 plus 15, or 29, and 35 minus 6, or also 29i. And that's how you handle multiplication. So you can do multiplication, and you can do addition, you can do subtraction. And the next question might be, can you handle division? And the answer to that is yes, but before we get to that, I actually do have one more concept that I have to introduce, which is called the conjugate. So, for some complex value a plus bi, the conjugate is the value a minus bi. And the reason why that's called the conjugate comes from the same sort of thing that you may have seen with equations, or not equations, expressions that have roots in them. You want to be able to cancel a term here. You want to be able to cancel that I, because this behaves something like a difference of squares, where what happens when you multiply it is you get a plus bi times a minus bi. The a's come together. You get a squared. You have an a plus bi minus an a plus bi. No abbeys for us. That gets killed. And then here you would have bi times minus bi. So you get minus bi squared or plus b squared. So that multiplication by the conjugate gets rid of the imaginary term. You're just left with a squared plus b squared in the same way that the difference of squares works. And you may find yourself wondering why introduce this before division. And to get to that, well, there's a little bit more to the story that we'll see next.